So here we're going to do an example of a separable equation. So if we want to solve them by separation, we typically are given, for these first order problems, some derivative. In this case, we're going to do derivative of y with respect to t. Could also be derivative of y with respect to x, whatever the independent variable happens to be. In this case, I'm going to set it equal to e to a certain power, let's say 2y minus 3t. So what's something to look for is to see, well, is this separable, right? And another way to think about that is, can I write this with all the y's on one side and everything multiplied by the dy, and all the t's on the other and everything multiplied by the dt? So sometimes you might get a little nervous when there's addition involved, which is a good thing, because sometimes when there's addition, you won't be able to get everything multiplied by your differentials there. But in this case, the addition is in the exponent, right? So when it's in the power, that is really, in our situation, equivalent to a multiplication. So let's rewrite that as dy dt is equal to e to the 2y times e to the negative 3t. So using the rules of exponents, this is a nice way of writing it out. So that's helpful then. If we want to write this in this on separate sides here, we can take everything with a y to the left by dividing. So, maybe write it down below if you want. That's equal to e to the negative 3t dt. What I'm actually going to do here is do one little move to make this a little bit easier to look at. Is just another rule of exponents to write the left side as e to the negative 2y dy is equal to e to the negative 3t dt. And what we want to do is to take an integral of both sides, right? And so that's really the whole goal, why we want the dy multiplying everything on the left and the dt multiplying everything on the right, so that we can take an integral of both sides. All right, so let's maybe get a different color here. Now, on the left side, taking an integral of e to the negative 2y, so we have basically, that's a little bit of a gross color. I'm going to lighten that up a bit. So e to the negative 2y, so since it's exponential, that's going to be in the integral each time. And recall, when you're integrating, because you're sort of using the chain rule backwards, you're going to end up dividing by negative 2y. And a way you could check that is if I took a derivative of this, I would have, by the chain rule, a negative 2y that comes down in front to cancel it out. All right, awesome. So this is equal to e to the negative 3t over negative 3. So this is fine so far, as long as we just remember to add some sort of a constant there. But a good thing to recall is that this is an implicit form, so we could do one better by turning this into some sort of explicit form. So a way we could do that is first by, I'm going to multiply negative 2 both sides, so e to the negative 2y is equal to 2 times e to the negative 3t over 3, so the negatives canceled here, plus, and here's a trick that you're going to see a lot, negative 2 times an arbitrary constant is still just an arbitrary constant, so is equal to this. Now, to get the 2y down, I'm going to take a natural log of both sides. So to do that, it would leave me with negative 2y on the left is equal to the natural log of 2 to the e to the negative 3t over 3 plus some arbitrary constant. I can't really simplify that in there because there's that addition, so just leave it as it is. And then lastly, we can say y then is equal to negative 1/2 natural log of this whole mess. And there you have it.